Section 4.7 is on optimization, and this is actually an entire field of study for mathematics because problems can be very complicated. But the types of problems we'll be looking at are fairly nice because they're essentially going to boil down to a combination of section 3.9 and 4.1. And the process is going to be something like, given a function to optimize, this would be called the objective function, we can use calculus to find a maximum or minimum solution on a given domain. Now, the domain could be simple or it could be somewhat more complicated, but typically we'll have an objective function and it'll be subject to some set of constraints. It'll be some other kind of function or possibly more functions, and we'll have a logical domain on which to study the problem. And the calculus we're going to be using is pretty much the same as we're going to be using the whole chapter. We're going to find critical points, take a derivative, and try to find an absolute maximum or minimum value on some domain. So for our first example, we'll look at something popular. So we'll suppose a box is to be made out of a square piece of material that measures 4 feet on each side. The box will be made by cutting squares out of each corner and folding up the flaps that are left over. And we want to determine the size of cuts, the squares that we have to cut out, that will maximize the volume of the box. So to start, we have a big square of material, and it's 4 feet on each side. And we're going to cut squares out of each corner like this. And then we're going to fold up the remaining flaps in order to form our box. So, since we want to maximize the volume of the box, that must mean that our objective is, of course, the volume of the box. And what will be the volume of our box? Well, if the length of the side of the square of the cut corners is x, let's see, I'm going to start with 4 minus 2x. That's going to be the length of the side of the base. And that'll be squared. That'll be the area of the base times the height, which will also be x, because if I fold up this flap over here, that's going to have a side length of x. And that will be the volume of my box. And this has a logical domain, and I say logical domain because I can plug in any x value to this and I'm going to get some kind of a number, but depending on which x values I plug in, that number might be negative, which doesn't make a whole lot of sense for a physical box. So I have to cut out something, so x has to be positive. Otherwise, I just have a very flat box with no volume. And I can only cut out up to 2 feet. Because if I cut a square of 2 feet out of each corner, then I'm going to have 4 squares of 2 feet, which is, I'm going to cut away the entire box. I'm not going to have a box left. So I could label these if I wanted. This would be my objective function. And I could say these here are the constraints. But it's really just a logical domain, and I don't have any additional constraints that are governing my problem. But since I want to maximize my objective function, I'll take a derivative. I'm going to use the product rule. 2 times 4 minus 2x times negative 2x times x plus 4 minus 2x squared times 1. And I'm going to want to set this equal to 0. Let's see if I can do this an easy way. I'll factor out 4 minus 2x first. That'll leave me with 2 times negative 2x times x. So that's negative 4x plus I'm going to have 1, 4 minus 2x left over. 4 minus 2x. This should be squared. Times negative 4x squared minus 2x plus 4. And I want to set this equal to 0 in order to find critical points. Well, here's one possible solution right over here, but let's try to factor this quadratic to see what my other solutions are. So I'll have negative 4x squared minus 2x plus 4 equals 0. Or I could rewrite this. If I divide by negative 2 from both sides, I'll have 2x squared plus x minus 2. I don't know if I can factor that, so I'll go ahead and use quadratic formula because that always works. I'll have negative 1 plus or minus the square root of b squared, that's 1 squared, minus 4 times a times c, 4 times 2 times negative 2, all over 2 times 2. So that's negative 1 plus or minus the square root of 1 plus 16, 17, all over 4. What a lovely number. And what did I have for my other factor here? If 4 minus 2x is equal to 0, that means 2x is equal to 4 or x is equal to 2. But I actually don't want x equals to 2 because that was at the very end of my domain. If I included x equal to 2, I would not have a box at all. And that's silly. So let's look at my other solutions. I have negative 1 minus the square root of 17 over 4. That's less than 0, which is outside of my domain. So I don't want that, which means I only have one possible solution, which is negative 1 plus the root of 17 all over 4. Fabulous. Now, I only have one critical number, so this is probably my answer, but there exist problems where, I get a critical number and I end up not having an answer out of that. So, there are two ways I can check my critical point. I could either use a number line, the first derivative test, or I could plug that number into the second derivative to find out if my function is concave up or concave down. But since I don't like negative 1 plus the square root of 17 all divided by 4, we can use the first derivative test to determine whether this critical number gives me a maximum or a minimum, because it's possible that it gives me the wrong version. But this critical number is definitely between 0 and 2, but in particular it's between 0 and 1, because negative 1 over 4 plus root 17 over 4 is bigger than negative 1 over 4 plus root 16 over 4, which is equal to 0, but root 17 over 4 is also strictly less than 2. So it's somewhere in here. So I can use 0 and 1 for my first derivative test. So v prime of 0 would be equal to 4 minus 2 times 0 times negative 4 times 0 squared minus 2 times 0 plus 4. And that's equal to, well, 16, which is positive. And v prime of 1 would be 4 minus 2 times negative 4 minus 2 plus 4, giving me 2 times negative 2, which is negative 4, which is less than 0. So I'm going down, which means for my first derivative test, I know that I have a maximum here, so this must represent my optimal solution. So I can say square cuts of side length 1 plus root 17 over 4, however small that is, provide the maximal volume box. And I can really optimize anything. I can optimize distances, I can optimize costs, volumes, surface areas, whatever you want. So for another example, let's do a cost. So our situation now is that a pipeline needs to be built between a refinery on the shore and a drilling rig, which is 10 miles down the shore and 3 miles out to sea. The cost of laying pipe on land is $2,000 per mile, and the cost of laying pipe underwater, or over water if you want to be picky, is $8,000 per mile. We need to find the path of the pipe which minimizes the cost. So we should draw a picture always to start with. We'll have the refinery here, and then 10 miles down the shore, and 3 miles out to sea is the drilling rig. Now, you might be tempted to say, well, the shortest distance between 2 points is a straight line. And yeah, sure it is. But the shortest distance doesn't necessarily represent the minimum cost, because this shortest distance path, that is all underwater, which is the most expensive route, potentially. Actually, I don't know if it's the most expensive route, but it is, underwater is the costlier of the two options. And potentially, we could maximize the amount of time we spend on the cheaper option and then go directly out to sea that way. That way we have 3 miles of expensive pipe and 10 miles of cheap pipe. But I still won't know if that is the cheapest possible option. In fact, the cheapest possible option will probably be some kind of a balance between the two, where I go some distance along the shore and then I speed out directly towards the drilling rig, which is out to sea. Now, there are technically other options. I could go on land, out past the drilling rig, and then come back, but that's obviously more expensive than the halfway option. So I need to lay down some variables here to determine how long each of these pipe segments are, because I need a function to determine the cost of hooking these two guys up. So let's say X here is the amount of pipe on land, and then H is the amount of pipe underwater. Now, I can label domains for each of these. X could be 0, and it can go all the way up to 10. H could be 0. H can never be 0, because I have to cross the water some way eventually. So H is at least 3, and it has a maximum value of this hypotenuse here. So let's see, Pythagorean theorem for 3 and 10 would be the square root of 109. Let's hope that's not our option. But how do I calculate H for the halfway option, where I have some on land and some off? Well, I can use another right triangle here, because this distance here will be 10 minus x. So x plus 10 minus x will be the full distance of 10, which means h is equal to, well, h squared is equal to 10 minus x squared plus 3 squared, which is 9, which means h is equal to the square root of 10 minus x quantity squared plus 9. And I don't know if it'll help, but I'll simplify it a little bit. This is 100 minus 20x plus x squared plus 9. So I have the square root of x squared minus 20x plus 109. Who knows if I'll be able to factor that. But these here would qualify as my constraints. These label the bounds of my problem, and I have a method of calculating one part based upon another part. And this is probably going to help me simplify my objective function. So what is my objective function? Well, the cost is going to be 2,000 times the amount of pipe on land, which is X, plus 8,000 times the amount of pipe underwater, which is H. But since I have a constraint here, I have a way to calculate H based on X. I can simplify my cost function to be in terms of a single variable, which is 8,000 times x squared minus 20x plus 109. So that right there is my objective function. And I want to minimize that. So I'll need to take a derivative with respect to x and find critical numbers for it. So c prime is equal to 2,000 plus 8,000 times the derivative of this square root guy will be 2x minus 20 all over 2 times the square root of x squared minus 20x. Let's try that again. 20x plus 109. I can simplify that slightly by canceling a 2 on the top and the bottom. But I want to take this guy and I want to set it equal to 0. So what I should do is set up a common denominator. So I'll have 2,000 times this ugly square root plus 8,000 x minus 80,000 all over that nasty square root. Now what I can do in this situation is I can just take the top half of the fraction and set that equal to 0, because 0 over anything will still end up giving me 0 as long as the denominator is not equal to 0. But I'm pretty sure I won't get a denominator equal to 0 because h has a minimum value of 3, and h is exactly what that denominator is. So I'll pretend to ignore it for a little bit, and I'll set this top half equal to 0. Now what I can do is I have a lot of zeros here, so I can divide both sides of my equation by 1,000. That's going to get rid of 3 zeros on everybody. And then I want to get rid of the square root, so I'll put the square root on one side alone and shove everything else to the opposite side. So I'll have 2 times the square root of x squared minus 20x plus 109 equals a positive 80 minus 8x. Now if I square both sides, the square root will be gone. So I'll have 4 times x squared minus 20x plus 109 equals 80 minus 8x quantity squared. And I just got to multiply all this out and get everything on one side. Fabulous. So I'll have to subtract 4x squared from both sides. And I'll have to add 80x to both sides. And I'll subtract 436 from both sides. I'll have 0 equals 5,964 minus 1,200x plus 60x squared. These numbers have not been nice to us. Excellent. I can divide both sides by 12 to get some smaller numbers. I'll have 497 minus 100x plus 5x squared. And I don't think I can do much better than that, so I guess we'll just have to use quadratic formula again. So x is equal to, let's rewrite this to help myself out, 5x squared minus 100x plus 497. So from quadratic formula, x will be 100 plus or minus the square root of 10,000 minus 4ac. That's 4 times 5 times 497, which I'll write as 20 times 497 and this is all over 2a, which is 10. Plugging right along. 497 times 20. What is that? 9,940. How convenient. So x is equal to 100 plus or minus the square root of 10,000 minus 9,940 all over 10, which is 100 plus or minus the square root of just 60 all over 10. 60 divided by 2 is 30, divided by 2 is 15. So this is 100 plus or minus 2 root 15 over 10. So this is 50 plus or minus the square root of 15 all over 5. What is this? These are my critical numbers for my cost function, which I was trying to optimize. Now, x had a domain from 0 up to 10. So let's see if any of these fall outside of my domain. Well, 50 plus the square root of 15 all over 5, that is bigger than 50 over 5, which is equal to 10. So I don't want that one, because it's too big. It's outside of my domain I set forth for x, which means I only have one critical number here. That will be 50 minus the square root of 15 all over 5. Now, that's certainly going to be less than 10, and I'm pretty sure that the square root of 15 is not bigger than 50, so this is also positive. Now, I want to test this critical number to see if it's a maximum or a minimum. We're looking for a minimum. And again, I could use the second derivative to find the concavity to compare, or I can use the first derivative test. Now, given my cost function, the derivative of my cost function is this fraction involving square roots everywhere. I'm again going to choose to use the first derivative test, because the second derivative would look kind of ugly. Well, one note crashed, so let's try to write this again. My cost derivative function was 2,000 plus 8,000 times x minus 10 all divided by the square root of x squared minus 20x plus 109. So somewhere between 0 and 10 is my critical number, and I don't have any other critical numbers between 0 and 10, and I don't have any problems with my domain from 0 to 10, so I'm just going to go ahead and plug in 0 and 10 to test my critical number. If I plug in 10, I'm going to have 2,000 plus 8,000 times 0 divided by something, 100 minus 200 plus 109, which is whatever, that part is 0. So I get 2,000, which is positive. And if I plug in 0, I get 2,000 plus 8,000 times 0 minus 10, all divided by the square root of 0 minus 0 plus 109, which is 2,000 minus 80,000 divided by the square root of 109, and this is definitely going to be a negative number. So I was positive here, so it's going up, and I was negative here, which means I was going down, which means this number represents a minimum, which means x equal to 50 minus the square root of 15 over 5 is a local minimum for the cost function. Now typically what I should do is also check the endpoints to see if either of those are smaller, but since I was trying to minimize, and I have only one critical point, only one spot where my derivative changes direction, my values for 0 and 10 are both going to be bigger than the local minimum I found for my critical point. So, since c prime is less than 0 on 0 to 50 minus the square root of 15 over 5, and c prime is bigger than 0 on 50 minus the square root of 15 over 5 up to 10, this number must be the absolute minimum. So in terms of our original question, I'm going to lay pipe on land for a distance of x equal to 50 minus the square root of 15 over 5 miles. And then I'll switch to underwater pipe for the remainder of that distance, where h is equal to the square root of 50 minus root 15 over 5 squared minus 20 times 50 minus root 15 over 5 plus 109 miles. Lovely number. But it's entirely possible that one of my solutions could have landed on an endpoint. For example, the cost of underwater pipe laying is determining how far I want to stay on land before switching to water. So if I made my underwater pipe laying significantly higher or my on-land pipe laying significantly cheaper, then I would have chosen an endpoint solution. I would have had to choose an endpoint solution where x would be equal to 10 and h would be equal to 3. This would be especially true if I gave an extreme scenario where the cost of laying pipe on land was free. Then my cost function would have been 8,000 times the square root of x squared minus 20x plus 109, because the cost on land would have been 0, so I'd have 0 times x. And then when I try to optimize this, I'll have c prime equal to 8,000 times x minus 10 all over this big square root. And when I set it equal to 0, I'll end up having 8,000 times x minus 10 equal to 0, which means x would have had to be equal to 10. But that's exactly on my endpoint. So problems like this exist. In fact, there's one in the textbook where you find your critical point, you're trying to minimize the time it takes to travel around a circular lake, and you do all this work to find your critical point, but you find out that your critical point actually gives you a maximum when you're looking for a minimum. And in that kind of situation, the minimum solution occurs on one of the endpoints. And so you should always check the endpoints in addition, especially if you do a bunch of work and you find out that your critical number gives you the opposite of what you were expecting. You should approach all of these problems the same way. You should try to identify your objective function, find the equation for the value which you're trying to optimize, lay out any constraints you have, any secondary equations or the domain of the variables that will make sense for the problem, and then you'll try to use those constraints to simplify your objective function if possible, kind of like the cost function I had here. I had two variables and I simplified it with one of the constraints. And then you're going to take a derivative, find critical points, and find out what the maximum value is. On the next video, we'll have Newton's method, which is an application of linear approximation in a way for estimating roots of functions.